Hi everyone, welcome to this video. This is part 2 of compressible flow simulation in Ansys Fluent. I'm going to set up and run this external compressible flow simulation here in Ansys Fluent. So in this tutorial, I'm going to set up and run a transonic turbulent flow simulation around the wing using this software Ansys Fluent, and we will learn how to configure compressible flow, apply aerodynamic boundary conditions, and use the K omega SST turbulent model. So without further delay, let's get started. So first of all, it is good to have a look on our geometry here. This is the whole domain that we have. I will just use display mesh here, or you can go to domain mesh and display. So I will click here, and then I'm going to show you the geometry, the wing here. So I will click the pressure valve here to disable this surface from all the surfaces, and then I can display. So we have the wing here, but I will select the edges to see the meshes also. So I will click on the edge and then display. So you will see here I have the geometry. Okay, so then I will select this box selection, zoom to area. Then I can zoom on the wing to have a look. So this is our polyhex core mesh that we have created in Fluent meshing in the previous video, the first video, part 1 of this series. So you will see the meshes on the surface, two sides of the wing, and also as you remember, we have had a BOI to create a finer mesh here after the wing. So that is our geometry and the mesh that you can see, the wing. So now I can go again to isometric view. Just let me show you one another small tips here. I can again go here and select the box near the airfoil. So if you actually you can use the right mouse button to prop for mesh information in this graphic window here. So if I click a right mouse button on any node in the mesh, information will be displayed in this console here, Ansys Fluent console, and it's about the associated zones including the name of the zone. So for example, I will click here and right click here. So as you see, you have some information regarding this place that I have right click on it. So this is, for example, wing top that I have right click on it. Here again, I have to one right click as you see here. So the information now it's related to the fluid symmetry and the ID and the other information, useful information. So this feature is especially useful when you have several zones of the same type and you want to distinguish between them quickly. Okay, so now I can close this window and then go to our setup. First of all, here in the general, I will keep all the settings, default settings here, and I will choose the pressure based. Actually, this pressure based with the coupled option for the pressure velocity coupling is a good alternative to density based solver for Ansys Fluent when dealing with application like this involving high speed aerodynamics with shocks. Actually, selection of the couple algorithm is made in the solution method task page in the solution setup. So we will go there later. Okay, so now it is time to select the required models here in this problem. Okay, so I will go to the outline view, and then under the model, I will open the energy first equation. Then I will enable the energy and then press on OK. And then next will be select our turbulence model. I can right click and edit or double click on the this option. Then we have access to viscous model. In this project, we are going to use the K omega 2 equation model with the SST K omega model. So I will retain this default for this setting and then press on OK and then close this viscous model. Next task is select and edit our material. So I will close this one and open the material. And so I need to change the fluid in the air. So I will right click and edit here. So now I have access to material and this air, and I can edit. So the default fluid material here is air, as you see, which is the working fluid in this problem also. The default setting needs to be modified here to account for the compressibility and variation of thermophysical properties with temperature here. So let me show you what we can do. First of all, in the density, I will select ideal gas. Just one point here. If in the model here you didn't activate the energy equation, if you choose the ideal gas, it will be automatically activate, and so this option will be displayed. I can show you, for example, here. If I disable again here, so you will see the thermal properties will be disappear, and I will just click OK. But if you select the ideal gas, the thermal properties also will be appear here. So it means that the energy equation now is activated and you have access to this one. But I will also, before that, select this energy equation. Okay, and then for the density, I will select the ideal gas for the density variation by temperature. Then I will keep this specific heat and thermal conductivity and molecular weight as the default, but I will change the viscosity to this option, throttle length, here. So the Sutherland law is an actually empirical formula used to calculate the dynamic viscosity of a gas as a function of temperature, as you will see here in this graph here. So it is especially useful in such problems, compressible flow simulation, like in the aerospace application, where gas actually like this the gas properties like this viscosity vary with the temperature, as you see. So here you see as temperature increases, viscosity also increases, but not linearly. It is a non-linear increase here. So I will keep all this setting here and then press on the OK here. Okay, that's it. But while these density and the viscosity have been made temperature dependent here, specific heat and thermal conductivity have been left constant, as I said before. So for high-speed compressible flow, thermal dependency of the physical properties is generally recommended. So here, for simplicity, thermal conductivity and CP here, specific heat, are assumed to be constant in this tutorial. but in your case, maybe you need to change these values also here. So now I have made some changes for density and viscosity. Now I can click on the change and create. So the air properties will be changed to these new settings, and now I can close this material dialog box. Okay, so now time is to go to check our boundary condition. So first of all, I will go to this boundary condition. Okay, so let's go one by one here. First of all, we have our inlet, and the inlet is a pressure far-field type. So we need to actually set up there. And this is pressure far-field, this green one. So for edit this part, I will open by double-clicking on the pressure far-field inlet boundary condition. We have a few items that we need to fill out. Okay, so this gauge pressure here in Ansys Fluent is always related to the operating pressure, which is defined in a separate input ledger. So I will keep and retain this value here to 0. And if I bring this slide here, I can put our Mach number here. So I will change this Mach number to 0.8395. If I check it again, 8395. And then after that, we need to put the direction here, and the coordinate system, I will retain the Cartesian here. But we need to change this value because we have angle of attack 3.06 here, so it is not directly in X direction. We have this X and Z direction here, so we need to change this actually direction and apply here. So this Mach number has two components in X and Z direction, so we will keep put here. So first of all, it is this is the X direction and this is Z direction. So I can just calculate 3.06. So for the X direction, which is the cosine of this 3.63, so I can select cosine. So it is 998574. So I can copy this value here and put in the X direction, and the same for the Z direction. So this time it's sine of this 3.06 degrees. So I can write 3.06, and this time it's a sine of this value. So I can copy and paste in the Z component direction, and so I will just change this to 2. Then I will, for the turbulence model, I will retain the intensity and viscosity ratio here, and also the value for this turbulence intensity and the viscosity ratio. The viscosity ratio here should be between 1 to 10 for the external flows. So I can keep this value here. And then I can go to the thermal tab here and change this value to ambient temperature to 55.56 to 55.56. And finally, I can apply here and then close this window. Okay, after that, to set the pressure, as I said here, I set gauge pressure to 0, so I need to go to the operation condition in the physics. I can find it. So under the solver, I have this operation condition. I can click to open this value, and then if we go again to this problem overview, so we have the uh, pressure here, so I can just write this value as 8600 for this operation pressure as the Pascal. So this operation pressure should be set to a meaningful mean value in order to avoid round-off errors. And the absolute pressure must be greater than 0 for compressible flow. So if you want to specify boundary conditions in terms of absolute pressure, so you can make this operation pressure as 0 and then change there. So now I can click on OK and then close this operation condition. So I will do OK. Now I will go to again physics, and under solver I will select the reference values here. So these reference values are used to non-dimensionalize physical quantities used for post-processing later. So the dimensionless pressure coefficient will be used in the future steps that you will see later. So in this window, compute from, I will select the pressure far field from this computer from drop-down list, and then Ansys Fluent will update this reference value as you saw based on the boundary condition at the far field boundary as we fill out. So you will see some like this temperature and this velocity also based on the Mach number. And I select the reference zone to Floyd here. Now it's time to switch to the solution. I mean, go to the solution. Okay, so I will click on the solution mode, or also you can go here. I will retain the other boundary condition as it is. So I will go to the solution, and under the solution, I will select methods here, or you can just double click here to open. So as I said before, we select pressure based. So the scheme here is coupled. So it's a pressure velocity coupling, and it is useful in this type of problem. So I will retain the others at the second order, and then I will enable some residual plotting during the calculation. So here under solution, under reports, I can select the residuals here. So I have this residual. So I will retain the settings here. Just ensure that this plot is enabled in this options group. So then you can just simply click on OK to close this window. And now time is to initialize our problem. So I can go to initialize here and then double click on initialization, or you can use here, and this is the hybrid. So I will retain all the settings as hybrid initialization here, and then click on the initialize here to start initializing. Okay, so this part is also done. We can write our case file and then start the calculation. So I will go to write case and then keep this name and with this format. So I will just click on OK, and then the file has been written in the working directory. Now it is time to go and run calculation. So under the solution, I have run calculation. I can double click here. You can also run your calculation from this top menu here. I will go from here. For this time scale factor, I will write 5 and then I enter 150 for this number of iteration. So regarding this time scale factor, so you see it's under the pseudo time setting, and so this pseudo-transient approach is a method that is used to stabilize the steady state CFD simulations like this one that we are going to. So the time scale factor actually allows you to further manipulate the computed time step size calculated by Ansys Fluent. So larger time steps, so as you see, I have increased this time scale factor to 5. So the larger time steps here can lead to faster convergence. However, if the time step is too large, it can lead to solution instability. So I just changed this value to 5, and now it's time to calculate on our solution. So I can click on the calculate button, and then we should wait a few minutes, and I will pause the video and come back again after the convergence. Okay, so now solution is converged, so I can click on OK and then write the data file, case and data, and then OK to overwrite on the previous case file. Okay, so the file has been saved, and you will see after 131 iterations, solution has been converged. So that's it for today's video. In the next video, part 3 of this video series, I will go through the post-processing of this transonic wing CFD simulation, again in Ansys Fluent, and we will check some Mach contours, shock waves, and other post-processing. So please follow the next videos, and I will see you in the next video. Thanks for watching.